motion and pressure. And the starting time is 8:36. And what's the goal of today? The goal of today is to learn the brain drawer study method, the 10 steps, right? That is the main goal actually. Learning motion and pressure is the byproduct. It's the byproduct. But the main goal is to get used to yourself on how this study method works on these 10 steps. And at the end of the 10 step, hopefully you're going to get 10 out of 10 in the MCQ. So that is your goal, right? That is your goal. Learning motion and pressure is a byproduct, right? So let's do step number 1 now. There are 4 drawers. There are 4 drawers: speed, fluid pressure, solid pressure, turning, and moments. Okay. This is the story that I created for you to be able to remember the name of the drawer easier. Speed. You know this very famous YouTube guy called Speed? Do you know? Eric, I think you should know, right? And Xuan, do you know? Yes, I think you know. Xuan, I think you know. Do you know? You do know. You also know. Okay, good. Yes. So I'm using him as one of the actor in our story. So Speed presses squid. Squid in Malaysia is in Malay word is sotong, but I'm using squid because it is sounds like fluid. And when he presses the squid, it becomes solid. Right, the squid become solid. Then both of them, the squid and also speed, take turn to play seesaw at Momoland. Right, so there are actually 2 actors here: the squid and also the speed, the YouTube influencer, the very famous YouTube influencer. And Speed so naughty, and he pressed the squid, and the squid becomes solid. And then both of them became friends, and they take turn play seesaw at Momoland. Momoland is like a playground, right? And the playground is having seesaw, and they take turn to do this seesaw up and down, up and down, up and down. All right. So speed represent drawer number 1, speed, obviously. Press squid is a pressure of the fluid, right? Becomes solid. All right, so solid pressure. And then take turn, turning. Play seesaw at Momoland. Momoland is moment. Seesaw is, you know seesaw, why I put seesaw later. But for now, just remember there's a seesaw there. Once you learn what is turning and what is moment, then you understand why seesaw is there. Seesaw needs to be there, right? All right. So that is step number 1. So let's go to step number 2. Step number 2, let me just widen this a bit. Right. Okay. Let's read this as usual. Read this, you may not fully understand what does it mean over here, but it's fine. Just understand that there are 4 drawers, and inside 4 drawers, each of them has different keynotes. Right, for speed, you have this keynotes 1, which is speed, and keynotes 2, which is the graph. Then for drawer 2, the fluid, you have gas, atmospheric, and liquid. Then for drawer 3, liquid, solid pressure, you have the definition of solid pressure and also the formula, the equations. Then for turning forces and moment, you have the equations, you have the explanation, and you have the center of gravity. Right. So let's take 2 minutes to read this. Okay, 1 more minute. Thirty more seconds. Okay. Now we are in step 2. Yeah. Sorry, I was being distracted because there are other students trying to log in and they cannot log in. So I have to send them the link again. Right. So let me continue here. Right. Let me refocus. Yeah. So Eric, can you tell me the story?
Speed presses squid becomes solid. Both take turn play seesaw at Momoland.
Right. Can you tell me the name of the 4 drawers?
Speed, speed, fluids pressure, solids pressure, turning in moments.
Right. Okay. So there are 4 drawers here. And these 4 drawers, we have speed, fluid pressure, solid pressure, turning, and moments. And speed, which is the YouTube influencer, press liquid. So now I want you to imagine this very, very famous guy right in front of you in your story. And he's playing with this squid. And he's pressing it so hard that this squid become a solid. Right? And then they both of them became friends, and they take turn to play seesaw at the Momoland. Right? That is helping you to remember the story, the name of the drawer in sequence. Right? So we've completed step 1 and step 2. Now let's continue step 3. Hi Jaden, hi Alice. So we will continue step 3. Right? Okay. So we'll divide it into 2 parts. This part 1 and 2. Right? As usual, you have to read this, and then you'll be able to use this as a reference to know, in fact, this particular part is an extension of this point number 1 in step number 2, right? So we are actually building Lego. We learn the key informations, and then from there, you might not fully understand the key informations now, but as we continue into the further steps, then this will give you more knowledge and information for you to be able to understand what drawer 1 is about, right? So just be patient, and let's start the first 1 minute for step number 3. 10 more seconds. Okay. Let me go back one step back for the benefit of Elise and Jaden, because I think this is important. If you miss this, then maybe you'll be doing catch up later, right? But I do not want you to do that. So if you have a pen or paper, and if you can write this down, or if you can do a screenshot, as long as there is way for you to refer when I talk about this main story, then it's fine, right? So imagine yourself, okay, imagine that there is this Speed, you know, this very famous YouTube influencer, and he's a very, curious and naughty boy, and he pressed on a squid, and that squid become solid. He pressed so hard that the squid become a solid. And then both of them became friends, and they take turn to play seesaw at Momoland. Okay, so that is a story to help you to remember the name of the drawers. So we have only 4 drawers: speed, fluid, pressure, solid pressure, turning, and moments. So speed obviously is to link it with drawer number 1. Presses, squid, so fluid, pressure, because squid sounds like fluid. Solid, so it became solid, so solid pressure, drawer number 3. Then drawer number 4 is both of them take turn, play seesaw at Momoland. Turning is the turn, Momoland is the moment, right? Drawing is here, okay. So Momoland is the moment, all right. So that's how you are able to remember the name of the drawers. There are 4 drawers. So Jovin, there are 4 drawers, okay? Remember there are 4 drawers, and this is the story. This is the story. If you can write it somewhere on a piece of paper right in front of you, because this is going to be your reference, right? We have already passed step 1 and step 2. Now we are in step 3, right? Step 3, where we just started it, and we finished reading this part. Now let's go to the second part of drawer number 1. Okay, let's do 1 minute. Okay, 10 more seconds. Right. Let me go back a bit here. The goal of this 2-hour session is to learn brain drawer study method. This science that we are learning, motion and pressure, is the byproduct of this 2 hours. And this brain drawer study method is the 10 steps. Now we are in step number 3. Then we are going to go into step 4, 5, 6 until number 10. Right. When you are familiar with this brain drawer study method, you can actually use it in other subjects, other chapters, even in history, geography, any other subjects. And now in order for me to teach you this method and to show you and to facilitate you, obviously I need to have a content. And for this case, I'm using science as a content to show you how brain drawer method works, right? And at the end, hopefully that we're gonna get 10 out of 10, the MCQ in step number 10, right? So drawer number 1 for step 3 is done. And basically there are 2 main key points over here. which are the speed, the definition of the speed, the formula of the speed, and the real world speed to have an idea what speed we are talking about relative to you when you're walking, and a cheetah which is running, the sound and the light, and what is the difference between instantaneous and average speed. And scientists usually rely on average speed more than instantaneous. Then what is relative speed, right? All of this you learn as we proceed into the next steps, right? Then you have distance versus time graph. And then you need to know what does it represent for the slope or the gradient of this graph. When it is stationary, what does it mean? And curve of the graph, what does it mean, right? So let's go to drawer number 2. Drawer number 2, we have, let's divide it into actually also 2 parts. Okay, for here, let's do 1 minute. Drawer number 2 is the fluid pressure, right? Speed press on the squid. Yeah, that is the drawer number 2. All right, so let's go to the second 2 points. Point 2 and point 3 in drawer number 2, the atmospheric and also liquid. The first point was about gas. Okay, atmospheric and also liquid. Let's do 1 minute. All right, let me explain a bit of the story of this drawer. Hot and squeezed gas, and you throw an atom bomb to the squid in deep ocean, and then this squid jump up thrust. So it's explaining hot and squeezed gas is explaining about the gas, right? Hot means the temperature, and squeeze is the volume being squeezed, lesser volume, then higher pressure of the gas. Atom bomb is to represent the atmospheric. Atom bomb, atmospheric, right? Then squid in bomb the squid. Squid is the liquid, sounds like liquid, and into a deep ocean and then upthrust. So liquid is about the depth. The deeper you go, the more pressure you're gonna get. Then there's upthrust. Upthrust is about the water pressure at the bottom of the object, just like ship. How ship is able to float on an ocean, on the sea, right? Because of this upthrust force, which you're gonna learn later. Yeah, I think you have already read this and you have some understanding about what is this upthrust, right? And the rest also, the depth of the liquid is affecting as a factor of the pressure, right? So this story is explaining a bit of what the keywords or the key concept that is in this drawer number 2. And drawer number 2 is fluid pressure. Let's go to drawer number 3. Right, let's start now. 1 minute. Ten more seconds. All right. Okay. Last one. Drawer number 4. Let's do 2 minutes. I think maybe this need a bit of a thinking. One more minute. Thirty seconds. All right, for those who have read it, if you have still haven't have your reference point, which is the story and the name of the drawer on a piece of paper, maybe you can take this as an opportunity to write this down and also write this down, because like I say, our brain needs an anchoring point, and this is the anchoring point that we are creating, right? So there are actually this as an anchoring point, and also each drawer, the story inside this each drawer as an anchoring point. Speed in Stanford every day, relax at the slope, flat ground and curve. I did not explain this just now. I missed this, but it's okay. We're gonna go to this in the step 6, right? So that is step 3, right? Before that, let's see. By now, you should at least know there are 4 drawers and the name of the 4 drawers. At least the name of the 4 drawers, without going into what do you know about this drawer, each of this drawer, right? You should know there's speed, fluid pressure, solid pressure, turning, and moments. That is the minimum, right? If after this, if now your daddy or your mommy asks you, what do you learn from, what's the time now? Now it's 8:30, we started at 8:36, and now it's about 9 o'clock, so it's about 20 to 25 minutes. What do you learn? At least you can tell him that you learn about speed, fluid pressure, solid pressure, turning and moments, right? So that is the minimum that you can, you have to know, right? Next is, if you're a bit more advanced, then you can explain what is speed. And then in the speed, you have the distance and time graph, right? And for the drawer number 2, you can talk about gas, atmospheric, and liquid pressure, right? Gas, atmospheric, and liquid pressure. And the story can help you to remember some of the informations or knowledge inside this drawer number 2. Then number 3 is the solid pressure. Papa used needle, poke his own finger. Right, Papa used needle, poke his own finger. Maybe this doesn't make any sense now, but later I hope as we go into step 6, you get more insights about how this story is related to this drawer. Then drawer number 4 is about the turning and moments, about the seesaw, about this formula, right? Now let's go to step number 4. Let's go to step number 4. How do you do this? Is you read these questions, and then you relate this is which drawer, right? And obviously this is drawer number 1 because I've already written over here. Okay, and then you read the answer and you compare it with your reference, which is here. Yeah, and most of the time the answer is going to have more details, more information compared to the step number 2, the points in step number 2, right? So let's start now. 1 minute. Question number 1. Okay, 1 minute is done. Okay, if you realize this question is about drawer number 1, speed. And from here, speed until the physical system is referring to this, the definition of the speed, the formula, and also the real world speed, right? But it is elaborating in more details. So this is how we build the Lego as our foundations, and build more knowledge on top of the foundation Lego. Right. Let's continue on question number 2 in 1 minute. Let's start now. Okay, 1 minute is done. So this question is also drawer 1, and it's helping you to think what is the difference between instantaneous speed, average speed, and relative speed or relative motion. All right, so these are the answers. So this is to explain this part. And next, question number 3 is drawer 3. Drawer 2. Drawer 2 is fluid pressure. Fluid pressure. Remember the squid that is being pressed? Right, so that is drawer number 2. Let's do 1 minute now. Ten seconds. All right, so this is talking about the pressure, volume, and altitude. How these three primary variables is affecting the pressure, the fluid pressure, whether it's gas or atmospheric. All right, so let's go to question number 4, which is also drawer number 2. Let's start now. Twenty seconds. Okay, drawer number 2 and is explaining this part, liquid, right? Drawer 3. Or quick question 5. Let's do 1 minute also. Ten more seconds. All right. Question 6. Let's do 1 minute. Oops. 10 more seconds. This is drawer 3, still in solid pressure. So by now you should understand high pressure, concentrated area, low pressure, distributed area. So if your area is small, then it's high pressure with the same force, right? Drawer number 4 for the next question. Last drawer. Okay, last questions before we do a quick revision later. Okay, this is drawer 4. This part, center of gravity. Ten more seconds. Okay, another one more round of this step number 2. Then we'll go for a quick break. Let's read this from drawer 1 until drawer 4 one more time, and then tell me. And I hope that you are able to understand this more compared to maybe 1 hour ago. When did we start? 8:36. Now it's 9:15. Less than 1 hour, maybe 40 minutes ago. Right? You should be able to understand more now by just reading this again. Let's start 1 minute. Ten more seconds. All right. Let me give you before we go for break. Let me give you a bit more information. Right now, what is this story about? Hopefully by now, if I explain the story, you can understand how is this story related to this drawer number 1, the content of drawer number 1 better. Speed in Stanford. Stanford is a university. Every day, relax at slope, flat ground, and curve. Right. So Speed is that YouTube guy. He is in Stanford every day and he's relaxing. So Speed is talking about the definition of a speed. Right. So in this drawer number 1, there is definition of a speed that you need to understand. And then Stanford is sounds like instantaneous. Everyday sounds like average. Relax, relative speed. So speed in Stanford, instantaneous, average, relative speed. So this is to give you an idea that these are the key information that you need to know, and help you to anchor that these are the key information that you will you need to explain when you're explaining drawer number 1, right? So what are the key information? You need to explain the speed. You need to explain the instantaneous versus average speed. You need to also explain the relative speed, right? So at slope, flat ground, and curve, this is the time, distance and time graph. What is the meaning of slope for distance and time? Is the speed. Flat ground means stationary, flat, right? So the graph of distance and time, when it's flat, it shows that it is not moving. It's like a horizontal line in the graph. Then curve means that it is acceleration or deceleration, depending on which curve that you are in. Okay, so that is the story. Then story number 2 is the hot and squeeze gas. Put an atom bomb on the squid in the deep ocean, and then it jumps up thrust, right? So hot and squeeze atom gas, gas is the factor that is affecting the gas pressure, temperature, and volume. So hot, temperature, squeeze, volume. Then we are talking about the gas pressure now. Then atom bomb is talking about the atmospheric pressure. Then liquid is squid, deep ocean, and then jump up thrust. So the depth of the liquid is affecting the pressure of the liquid pressure. And then also there's this upthrust factor that you need to understand. Why a Titanic that is a thousand of tons of a ship having so many things inside is not sinking compared to a block of aluminium or a block of metal that is only 2 kg is sink into the water, right? So this is upthrust. Then solid, Papa used needle, poke his finger. So this is about the solid pressure. It's about the force and also the area, right? And then turning forces and moment, turning forces and moments. Big apple and small pan take turn play seesaw at Momoland. So big apple and small pan. Pan, big and small, you know it later. Okay, it's going to no, I'll tell you now. Right. So imagine there's a big apple and also a small pan. They are playing seesaw. Right. Obviously, the big apple is most of the time is going to be easier to play the seesaw because he's a big apple. He's the weight. He's having a big mass that is able to control the movement of the seesaw. Right. So big apple and small pan, and is playing the seesaw. Right. Why do I put a pan there? Because to reflect the perpendicular distance. Right. Later you will know more why is this important if you do not understand it now yet on this formula. Moment equivalent to force times perpendicular distance from the pivot, which is the meter. Right. So a big apple and a small pan take turn to play seesaw at Momoland. Momoland is the moment. Seesaw is the you're gonna see a lot of example on the seesaw related to explaining turning forces and moment. Right. So that is the revisions. Let's take 5 minutes break. Xuan, if you need to go now, you can go now, or if you want to stay a bit longer, it's fine. Let's start now because Xuan is having an event that she has to attend. So let's go for water break. Okay, 1 more minute. Is everyone back? Can you have a show me a show of thumbs up if you are back? No one is back yet. Show me a thumbs up if you are back. Mm. Jolene, are you back? Eric, are you back? Can you hear me? Yeah, Eric is back. Elise, are you back?
Yes.
All right. Jaden? Jovin? Yes, Jaden's back. Jovin's back. Xuan, I'm not sure you are still here because you told me you are attending another event. Okay. I assume she left. Okay. Now, I think by now, we already completed this step 1, 2, 3, and 4. We are going to step 5. Okay. See you soon. I'll send you the link. Bye-bye, Xuan. Right. I'll send. Yep. So we'll continue on step 5. Right. We'll continue on step 5. And remember the 4 drawers. We have 4 drawers: speed, fluid pressure, solid pressure, turning forces, and moment. How do you remember these 4 drawers? With this very simple and silly story. Imagine speed is in front of you and he's pressing very hard on this squid. And this squid suddenly became solid. And then both of them, the squid and also Speed, this Mr. Speed, take turn to play seesaw at Momoland. Right? This is to help you to remember these 4 drawers. All right. So let's continue here. Step 5, drawer 1, 1 minute. Ten more seconds. Okay. If you realize, this is point number 1. This is point number 1 here. Together with this average instantaneous velocity until here, relative motions. This is point number 1 here. Okay. So let's take another 1 minute to continue to finish to finish up the remaining of this point number 1. 10 more seconds. Right. If I relate this with the story, is until here. Right. Point number 1 is until here. Speed in Stanford, every day, relax. Speed, instantaneous average speed, relative speed. Speed in Stanford, every day, relax. So imagine this speed. He is now in Stanford University and every day relaxing. Right. Next, point number 2. Point number 2, before we go to drawer number 2. Okay, let's start now. Let's read here until here. Okay, 5 more minutes, 5 more seconds. Done. So this point number 2 is related to this point, distance and graph, a distance time graph, right? And this is, if you are relating it to the story, is slope, flat, and curve. Slope, stationary is like flat, horizontal line, and curve, right? So this is the explanation, more explanation about the slope, flat, and curve. Slope, flat, and curve, right? So this is drawer number 1, speed. Now let's move on to drawer number 2. This drawer number 3. Okay, look, move on to drawer number 2. We will divide into 2 parts. Here until here, 1 minute. Gas and atmospheric. Ten more seconds. Okay, let's continue on the remaining of this drawer number 2. Okay, this is liquid. Those who want to read again on the atmosphere, you can read again. So liquid is about the depth and also the upthrust. Right? Drawer 3, this part here. Drawer 3 is the solid pressure. Solid pressure. So the squid became solid, right? Remember? The squid became solid. 1 minute. Drawer 3. Ten more seconds. Okay. The story is Papa uses needle and poke his finger. Papa is representing the Pascal or pressure. You can use both ways. Needles also can be representing two things. One is the force, the Newton. N is actually Newton. And needle, you can also think it as, the needle, the pressure is very high because the area is very small. So when the area is very small, with the same with the force that is being exerted into the needle, you can easily poke your finger and to the level that you will break your skin. All right. So Papa uses a needle and poke his finger. Drawer number 5. Okay, this part here. Let's do 1 minute and 30 seconds. Second left. All right. So here we completed step 5. Now we're going to step 6. Right. Step 6 is creating the story. We have already explained the story as we go from step 3 until step 5. So this will be easier steps for you to go through. Right. Step 1, speed. The name of the story drawer is Speed, and the story is Speed in Stanford at university. Every day he's relaxing at slope, flat ground, and curved ground. Right. So by just looking into this story, you can already know what are the key points that is in this drawer. It's about the definition of the speed. It's about instantaneous speed, average speed, and relative speed, right? So that is the anchoring point. And from there, you can explain what is instantaneous speed and what is average speed and what is relative motion or relative speed, right? Then also there's information that you need to understand about the slope, flat ground, and curve. What is this? This is the distance versus time graph. So you need to explain what is this slope in this graph? And what is this stationary or horizontal line in this graph? What does it mean? And curve, what does it mean? It means acceleration or deceleration. The slope means the velocity or the speed, right? For this distance versus time graph. And then flat ground means it is not moving, it is stationary. Then same goes to drawer number 2, where you have hot and squeezed gas activated at this atom bomb to the squid in deep ocean and then jump upthrust, right? And the squid jump, it went into a deep ocean and then jump. How is it related to the content of the drawer? Hot and squeezed gas. You remember we have 3 type of pressure that we need to learn in this drawer. We have the gas, we have the atmospheric, and also we have the liquid, right? So hot and squeezed gas is about, you know, the temperature and also the volume. It's going to have a factor of identifying the pressure of the gas. Then atom bomb is addressing the atmospheric pressure. So the atmospheric pressure is decreases with the altitude because the gravity pulls most air particle closer to the air, to the earth, right? So making the air less dense at higher heights. Then the next thing that you need to remember is the squid. Squid, deep ocean, and jump upthrust. What does it mean? So there's this liquid pressure that you need to know, and there's a factor that's affecting this liquid pressure related to the depth of the liquid. The deeper you go into the liquid, the higher the pressure that you're gonna feel. And then this upthrust. Upthrust is explaining why a big ship like Titanic is not sink into the ocean, right? Then drawer number 3, solid pressure. Papa uses needle, poke his finger. So there's Pascal, there is Newton, and poke his finger. There's something related to the force and also the area, right? And then drawer number 4, turning forces and moment. Big Apple and Small Pan, they are playing seesaw, taking turn to play seesaw at Momoland, right? So big and small, and also big and small is talking about this this seesaw, right? The Big Apple and the Small Pan, they are not at the same length of the pivot point of this seesaw. And then pan is to represent the perpendicular, right? The distance need to be calculated based on the perpendicular of this pivot. And then take turn. Turn is what? Turn is the turning forces. And play seesaw at Momoland. Momoland is moments. And seesaw is the example to explain these turning forces and also moments, right? So you have this story here. Speed in the University of Stanford, relaxing, and every day relaxing, and he's relaxing at the slope, and also even on the flat ground, and also even on the cliff. Then this fluid pressure, this atomic hot squeeze atomic bomb to the squid, and then he went into the ocean, deep ocean, and then upthrust it back up. Then this is your papa and his finger, he poked his finger. And this is the Momoland with this Big Apple and Small Pan, right? So that is step 6. This is your reference point, right? So there are 2 reference points. One is this story, and the other one is this part, right? If you are able to write it down on a piece of paper right in front of you, and that is your reference point that you use for your MCQ, right? And also for the quiz or for the video, right? Now let's go to step number 7. Step number 7. I hope everyone is still following. No one fell asleep. However, because I cannot see you, so I do not know how excited or how not excited you feel. But I hope you are able to follow this, because it's not the first time that you are attending the brain drawer class. And following these steps should be should be easy by now, right? So now step number 7, answer quiz. This is, there's one question, there are 10 questions. So first question, you read it and then you ask yourself which drawer is this related to, right? I make it easy for you. In fact, for this chapter, I put it on top, what is the drawer, right? So you can also get this as a reference. Then form your own answer before you read this answer. Once you form your answer within like 5 seconds, 10 seconds, then you read this answer and you see whether your answer is similar to this. If not, then pick the new information that is in this answer and put it inside your drawer. Okay, so let's do 1 minute for 2 questions. Let's start now. Read the questions, what drawer, form your own answer within seconds, then compare your answer with the answer provided. Okay, let me pause a bit before I go to question 3 and question 4. Why this is important? Why this is important? Remember, what is important? Why having you to form your own answer is important? Remember, I told you the difference between smart student and also not so smart student. So the version A of yourself and the version B of yourself. So let's take version A is the smarter version of yourself and version B is yourself now, right? Obviously, you want to be a smarter person of yourself every day, right? To increase every day, right? So the difference here is, number 1 is the knowledge base. Version A of Elise is having a bigger knowledge base than version B of Elise. Number 2 is the speed of retrieving the information inside your knowledge base. Version A of Eric is having the ability, the speed to retrieve information faster than version B of Eric, right? Number 3 is the ability to identify new information and then store it in your knowledge base. So version A of Jaden is able to identify the new information that you do not have in your drawer and put it and store it inside the right drawer systematically in an organized way. Compared to version B. Version B of Jaden, he's not having this ability, right? So this exercise that we are doing right now to build your own answer, that means what? That means you have to retrieve your answer from your reference. Your reference is either here as your reference or the piece of paper in front of you as your reference, right? The more you do this, the faster you are able to retrieve informations, right? That's point number. That's first. That's the one of the skill. The second skill is when you read this answer, and there are new information that is not inside the answer that you created just now, and that is the ability to identify the Jaden's ability to identify the new information and then store it inside your knowledge base, so your knowledge base become bigger and bigger and bigger, right? Okay, I hope this is clear why we are doing this. Okay, so let's continue on our drill, question 3 and question 4 in 1 minute. 10 seconds. Okay. 5 and 6. We are still in drawer 2. Drawer 2 is the fluid pressure. Ten more seconds. Okay. 7 and 8. 1 minute. Drawer 3. Ten more seconds. Okay, last one. Before we go to the watch video, the easiest part of the entire band drawer. Okay, 10 more seconds. All right. Okay, let me ask you, how many of you? 1, 2, 3, 4. 4. Can each of you tell me one name of the drawer? Let's start with Eric. Eric, drawer number 1. What's the name of the drawer?
Drawer number 1 is speed.
Speed. Okay. Jaden, drawer number 2.
Oh, I cannot see the board. I can't see the questions.
No. My question is, what is drawer number 2? What's the name of drawer number 2?
Wrong number.
Eric, do you want to help Jaden? What's the name of drawer number 2?
Atmospheric pressure.
Fluid pressure. Yes, good. Elise, what's drawer number 3?
Solid pressure.
Jovin, last one.
Turning forces and moments.
All right. Okay. So there are 4 drawers, and you remember the name of the 4 drawers, right? And I hope by now you also remember what you have learned in each of the drawer, right? So we can take 1 minute before we go to the video. We take 1 minute to read from drawer 1 until this above the pivot, right? Let's start now. Ten more seconds. Right. So I think you also have the same feeling like me. We started at about 8:36 and we read step 2 maybe about 8:40, about 1 hour, slightly more than 1 hour ago. And now when you read this again, I believe that you are able to understand this more than what you have read it the first time, right? What I'm trying to say here is there's nothing changed over here. The only thing changed is you went through from step 2 to now step 6. You finished step 2 to step 6, and that's the only thing changed. And because of that, now you are able to understand the chapter more. And the chapter is motion and pressure. Okay? And now let's go to watching the video.
All right, let's jump right in. Take a look at this cheetah.
Can you hear the
It's
lady?
sprinting at over.
Can you give a thumbs up?
Yes.
Okay, Jovin got it. Eric, Elise, Jaden.
Yes.
Okay, let's do it. 7 minutes. Let's start now.
All right, let's jump right in. Take a look at this cheetah. It's sprinting at over 100 kilometers an hour. So what on earth could that possibly have in common with, well, with this? Yeah, a scuba diver deep down exploring a coral reef with the weight of the whole ocean above them. Okay, weird connection, right? But what about this? That iconic footprint on the moon, still perfectly preserved. How does that fit in? And to top it all off, let's throw this into the mix. A tightrope walker, balancing with incredible precision. A cheetah, a diver, a footprint on the moon, and now this. I know, it seems like a random collection of things, doesn't it? But believe it or not, there's a common thread. The answer to what connects all of them? Well, it's all about motion and pressure. These are the fundamental physics principles that shape pretty much everything in our everyday lives. And that's exactly what we're going to unpack today. So yeah, what do they have in common? It's pretty amazing when you think about it. They are all governed by the very same fundamental principles. The same rules apply to all of them. So here's our game plan. First up, we're going to figure out what fast actually means. Then we'll take a plunge into the invisible world of pressure, both in gases and liquids. After that, we'll see how that pressure works on solids, think footprints. And finally, we'll reveal the secret of a simple machine you use all the time, the lever. All right, let's get started. Section 1. How fast is fast?
Drawer 1.
It's time to really understand what speed is all about. So, what is speed, really? Well, in physics, it's super simple. It's just a way to measure how far something moves in a certain amount of time. The formula is as basic as it gets. Speed equals the distance you traveled divided by the time it took to travel it. Seriously, that's it. And that one little equation is behind pretty much all motion. And to give you a sense of scale, check this out. You know, a brisk walk is about 6 kilometers an hour. That cheetah we saw, a blistering 119. But then you get to an airplane at over 900. And then things get wild. Look at the speed of sound and then the speed of light. It's just astronomical. Kind of puts your morning jog into perspective, huh? Okay, but here's a really important little detail. There are two types of speed we talk about. You've got instantaneous speed. That's what your car's speedometer shows you, your speed right this second. But then there's average speed. That's your total distance for a whole trip divided by the total time it took. It's how you'd figure out if your road trip was faster this year than last year. You know, a great way to visualize risks is with a distance time graph. Think of it like a story of a journey. The steepness of the line, the slope, tells you how fast you're going. A really steep line means you're flying. A gentle slope means you're taking it easy. And a totally flat line, well, that means you've stopped for a snack. You're stationary. Okay, so we've got a good grip on speed. Now, let's move on to our next big topic, pressure.
Drawer 2.
We're going to talk about those invisible forces all around us, in the air we breathe and the water we swim in. Whoa, just look at the difference here. On one side, you have a perfectly normal polystyrene cup. On the other, that's what happens to the same kind of cup when you take it deep, deep into the ocean. We're talking 3,000 meters down. It's just crushed. That is the unbelievable power of water pressure, caused by the sheer weight of all that water pushing down. So what's actually happening here? What is pressure? If you could zoom in to a microscopic level, you'd see billions of tiny particles, molecules, just buzzing around and constantly slamming into surfaces. That constant bombardment is what we feel as pressure. And here's the cool part. In fluids like air or water, that pressure pushes in every single direction at once. And if you want to crank up the pressure in a gas, you've got two main tricks. 1, add heat. That makes the particles zip around faster so they hit the walls harder and more often. Bam, more pressure. 2, shrink the container. Give those particles less room to roam and they'll naturally bump into the walls more frequently. Again, more pressure. And this is the exact same idea behind atmospheric pressure. You know, the weight of the air all around us. Think about climbing a tall mountain. As you go higher, the air gets thinner, right? That literally means there are fewer air particles above you. Less stuff pushing down means less pressure. It's that simple. All right, we've covered gases and liquids. Now let's bring it back to solid ground. How does pressure
Drawer
work on
3,
solids?
solid pressure.
Let's go back to that footprint we saw on the moon. The formula here is key. Pressure equals force divided by area. Now the force part is pretty straightforward, but the area, that's where the magic happens. Because you can have the exact same force creating totally different amounts of pressure, and it all comes down to how big or small the area is. And this is the perfect example. Look at the snowshoes. They take your body weight, your force, and spread it out over a huge area. The result? Low pressure, so you float on top of the snow. Now look at the studs on that boot. They take the exact same body weight and concentrate it onto a few tiny points. The result? Insanely high pressure that bites into the ground and gives you grip. Same force, completely opposite outcomes, all because of area. Okay, on to our final topic, and
Last
this one
row.
is a secret of physics that you use probably dozens of times a day. We're talking about the physics of turning things, the science of levers, and what we call moments. So this turning effect of a force has a special name, a moment. The best way to think about it is opening a door. The hinges are the pivots. You push on the handle, which is as far away from the hinges as possible. The moment is the force of your push multiplied by the distance to the hinges. That's why the handle is where it is. Try pushing a door open right next to the hinge. You have to shove like crazy to get it to move. And this little setup with the apples shows it perfectly. How can that little apple balance the big, heavy one? Easy. It's further away from the pivot. Its small force is multiplied by a big distance. The big apple has a big force, but a small distance. The two moments cancel each other out, and everything is in perfect balance. So let's do a quick recap. What have we learned? Speed is just distance divided by time, and graphs can tell the whole story. Pressure in fluids, like air and water, that's all about particles bumping into stuff. Pressure on solids, it's a game of force times an area. And moments, they're the turning forces that make our world go round. Literally. So, from a cheetah sprint to the air pressure in your tires, these forces are everywhere, shaping everything. The real takeaway here is that you're now equipped to see them. So the question isn't just what they are, but where are you going to spot them next?
All right. Interesting questions. So let's continue on the next step, the last, almost the last step, which is the podcast. It's about only 4 minutes.
Welcome to our latest
Okay, so I will be highlighting the part that the lady and the gentleman is discussing.
deep dive. Today, we are looking into the hidden rulebook of the physical universe just acting all around you.
Right. And we are unpacking those big aha moments from some source material on motion and pressure.
Exactly. We are skipping the dry textbook formulas to bring you the actual physics of your everyday life. So, let's just start with speed. You look at your car speedometer, and that is your instantaneous speed right at that exact second.
Yeah, whereas your average speed is completely different. I mean, that is your total distance divided by total time, like pacing yourself for a marathon.
Right. But the really wild thing is relative motion. If we are driving side by side on the highway at exactly 70 miles an hour, physics says our relative speed is 0. We are totally still compared to each other.
It is a massive illusion, but your brain just accepts it. And if you graph that movement out, a steady speed is just a straight, steep line on a distance time graph.
And a perfectly horizontal line means you are totally stationary.
Exactly.
Yeah.
But the real story happens when that line starts to curve.
Because a curve means the speed is constantly changing. It is accelerating. Like dropping a ball from a window, it doesn't just fall at one constant speed.
No, gravity actively grabs it and accelerates it so it covers more distance every single second it falls.
And gravity doesn't just pull on solid objects like a dropping ball. It is actively pulling down on our entire atmosphere, which brings us to gas pressure.
Yeah, which we usually forget is really just billions of microscopic molecules constantly slamming into surfaces.
Right. And since gravity pulls the bulk of those air particles down towards sea level, when you climb a mountain, you are walking into air that is literally less dense.
Fewer molecules mean fewer collisions.
So you get a massive drop in atmospheric pressure.
But when you switch over to liquid pressure, the game changes entirely because water is completely incompressible. You just cannot squeeze it.
Meaning the deeper you go, the weight of all that water pushing down creates immense pressure.
Which is why engineers have to build dams significantly thicker at the bottom than at the top. They have to hold back an exponentially stronger force down deep.
That same depth to pressure difference is actually what creates upthrust, right? Because the pressure at the bottom of an object is higher than at the top.
Exactly. That upward push is the only reason a million-ton steel supertanker can stay afloat. The upward pressure is stronger than the downward weight.
So that is fluids, but solid pressure is a bit different. It is all about how force is distributed over an area.
Force divided by area measured in pascals.
Right. So picture an incredibly heavy earth mover. It doesn't instantly sink into soft mud because its wide tracks spread out that immense weight.
Creating very low pressure. But then you have a lightweight hockey player wearing cleats. They concentrate their whole body weight onto a few tiny studs on their shoes.
Which creates a massive concentrated pressure to pierce the turf for grip.
You even see this off-world. Think about Neil Armstrong's footprints on the moon.
Oh yeah, his body weight combined with his heavy spacesuit pressed down onto the very limited area of his boot treads, leaving a high-pressure stamp in the lunar dust.
And we usually think of force pushing straight down like that. But force can also create a spin. In physics, the turning effect of a force around a pivot is what we call a moment.
Like pushing a heavy door open on its hinges or the law of moments on a seesaw.
Right, a heavy parent and a lighter child can easily balance a seesaw.
They just have to find equilibrium by adjusting their distance from the pivot.
Yes, the parent sits much closer to the center, the child sits further out on the edge, and their clockwise and anti-clockwise turning forces match perfectly.
You feel this turning force every time you lean back in your office chair. All your weight acts through your center of gravity.
And if you lean back just a little too far,
Your center of gravity shifts right past the pivot point on the back legs of the chair.
creating an unbalanced turning force, and down you go.
It is wild how motion, fluid dynamics, solid pressure, and balance all connect like that.
They're just unseen, predictable rules governing everything we do.
Before we wrap up this deep dive, here is a final puzzle for you to mull over. How liquid upthrust depends on gravity creating higher pressure at the bottom of an object. So how do fluids and buoyancy behave for astronauts aboard the International Space Station, where they are in constant free fall and there is no up or down?
That is a fascinating question to leave them with.
Keep wondering about that, and we will catch you on our next deep dive.
Right. So here's where we completed our step 9. I think by now it's getting clearer and clearer of what is this chapter about, especially if we divide it into these 4 drawers. Now let's do our test. Let's open a new one and upload this book and ask him to provide us create 10 MCQ to show that I understand the chapter well based on this sequence. 1 is what? Speed. 2 is fluid pressure. 3 is what? 3 is solid because the squid turned into solid. 4 is what? They take turn and play seesaw. Okay, number 4. Okay, provide 2 question at once. Harder questions. Okay, I think for the last class, the question was too easy. Let's make it harder. Without giving me the answers in the question. Okay. So you have 2 reference. One is this as your reference, the keynotes, and the other one is your A4 paper. Okay, looks like it's a more difficult questions. So let's do the same drill. We do in this format. Let's say question 1, drawer what? Drawer, let's say drawer 1, and answer, let's say is E. We do it like this, okay? So we have question 1 and question 2. And Eric, Elise, and Jaden, you can type in your answer based on that format in the chat. Right. A drone travels and then which statement is correct? One D. Elise and Jaden, we are waiting for you. Give a guess.
I
Give a
can't
try.
see the.
Hmm?
I can't see the screen.
You cannot see the screen? Oops.
Yes.
Okay, let me. But are you able to see the screen for the past 2 hours?
Yeah.
Only this one, right? Let me do it again. Okay, are you able to see the screen now, Jaden?
No. No.
Still no?
No. Should I leave and rejoin?
If you can try. Okay, Jaden is back. Is it better now?
Yes.
You can see the screen. Excellent, excellent. So question 1 and question 2. Let's see. 1 is what? 1 is D by Eric. Elise, yours is question 2, draw 1, and answer D, right? So 2 is D. For Eric is B. Okay, what do I think? Two cyclists travel on a straight road. Cyclist A to the east, cyclist B to the west. What is the relative speed of cyclist A with respect to cyclist B? Okay. Jaden, what do you think? I think is B. I'm also learning together with you, by the way. Like I say, I'm teaching you the study method. I learned this chapter a few days before you, using this study method, which works for me. Why B is because one is east, one is west. So they're at the opposite direction. So relative speed is about speed relative to the observer. Let's see whether me and Eric get it right. Okay. Right. Okay. So this is the answer. At least this is the answer. And I think question 1, everyone got it right. Okay. So let's go to question 3 and question 4. Let's try. Eric, Elise, Jaden, let's try. Even myself. A sealed container of gas is heated while its volume remains constant. What happened to the gas pressure inside the container? This is drawing number 2. Right, this part. Anyone want to give a try? Volume remain constant, but it's heated. What happened to the pressure of the gas? Pressure decrease because molecules spread further apart. Pressure stay the same because volume is constant. Pressure increase because molecule collide with the wall more often. Pressure decrease because molecule loses energy. Elise, you type C. C is for question 3. Okay,
Yeah.
I assume it's 3 drawer 2 C like this. Okay. Yeah. Okay. What about 4? Atmosphere. And wait for Eric and Jaden. Atmospheric pressure at sea level is higher than on the mountain because air molecule is heavier at sea level. There are more air particles above you. Gravity is weaker on the mountain. Oxygen concentration is higher. Okay, Eric also C. For number 3 question. Number 4. By the way, this is a harder question. In fact, I should not write harder. I should write, give me IGCSE questions. Okay, maybe next time. D. Eric says it's D. Do you agree? Do you agree? I think it's B. What do you think? Elise and Jaden. Elise also thinks that it is D. Okay, what about you, Jaden? Why do I think it is not D? Is because the air is not only having oxygen. The air is having oxygen, nitrogen, carbon dioxide. So B is reflecting more of a correct answer because more air particles above you at sea level. That's what I think. More air particle means more concentration. Means more concentration. Let's see who is correct. I'll put B for now because it's 2/2. Let's see, is B or D? Okay. Yes, it's B. Right? Okay, we ask him why question 4 is not D as answer. Right. Atmospheric pressure depends on how many air particles are above you pressing down. Texo explained that as you go up a mountain, air density decreases, there are fewer gas particles, therefore pressure becomes smaller. Why B is correct? Right. Okay, then why D is wrong? Okay. Percentage of oxygen is almost the same because air composition is roughly constant. So the concentration of oxygen is about the same. It's still 21%. All right. I think, does it make sense? If it is, then we go to question 5 and 6. Okay. Let's see. 5. A person weighing 800 Newton stands on one foot with an area of 200 cm square. What pressure do they exert on the ground? So there's this formula, this equation, right? So I have to use this equation, right? What pressure? So it's force 800 divided by 200. 4 is, what about 5? Anyone want to answer? 5? Let me try 6. Two of the same force on the ground. Object A has twice the contact area. That means the area is bigger of object B. Which statement is correct? Object A produces twice the pressure. Object B produces twice the pressure. Okay. Anyone want to try? Give a try. Hurry up, give a try. Eric, Elise, Jaden. This is drawer 3, solid pressure. All right. So Elise is saying B, solid pressure. 6 is C. Both produce the same pressure. Eric, 5 is B also. What about 6? Okay, let me decode this a bit more. 2 objects. Okay, Eric thinks is B. All right. 2 objects, A and B. A is having twice the contact area. So A is having 2 times the area. So let's imagine object B is the needle, and object A is, let's say it's not twice, it's much bigger. The object A is your finger. Yeah. If the force that is being forced into the push on the needle to your feet, and your finger, the same force push on your feet, which one will have more pressure? Which one will make you feel more pain? The needle or the finger? Okay, Jaden says it's A. All right, which one will make you feel more pain? The same force that you push on the needle and the same force that you use your finger to push, and you exert that pressure into your, let's say, your feet. Which one will you feel more pain? The finger or the needle? Elise, which one will feel more pain? The needle, right? The needle will have more pain on your feet compared to, let's say, your finger. Right, so what does it mean? It means that the needle is having more pressure into your feet compared to your finger, even though the same force is being applied on your finger and on the needle. Right. So object A is what? Object A is your finger. Object B is the needle. Which statement is correct? Let's say object A is a finger, object B is the needle. Object A produces twice the pressure. Does the finger produce more pain compared to the needle? Because having more pressure means more pain. So it doesn't. Object B produces more pressure. Does the needle produce more pressure compared to the finger? Does the needle produce more pain compared to the finger? Yes, right. So I think it's B. Okay. Then explain answer for question 6. Right, B is correct for question A. 6. Let's say B is also correct. Let's read the answer. Right. I will not read it out loud. I will let you read. Then I'll scroll down. Okay. All right. I think this is clear. So question 7 and question 8. What is the answer? This is turning force. This is the drawer number 4. A force of 4 Newton is applied 0.5 meter from the pivot. Remember this formula. What is the moment produced? Oh, exactly. Right. So it's using this formula. Okay, let's go to number 8. 2 forces act on the seesaw. Left side, right side. What will happen? Okay, which one is heavier? Okay, I have the answer. Let's see my answer is correct. But I want to know your answers. Okay. Question 7, drawer 4. Answer is A. What about the rest? Jaden, you need to be faster. Right? Question 7 is using this formula. Jaden also thinks that 7 is A. Yes, me too. So the force is 40 Newton multiplied by the perpendicular distance, which is this one, 0.5 from the pivot. So 40 times 0.5 is 20. Number 8, Eric thinks that it is C. What do you think, Jaden and Elise? Remember, this is the seesaw. You are sitting on one side of the seesaw, and Eric is sitting on another side of the seesaw. How do you calculate the moment? You also think that is C. Okay. What about Jaden? Jaden has been a bit quiet. For question 8. Right? So how do you imagine this? I think it's C also, because 300 times 0.4 and 200 times 0.6 is the same answer. Right, let's wait for Jaden. C, okay. I think so. Right, so this is the answer. 40 times 0.5, 20. Moment, the law of moments. 300 times 0.4 and 200 times 0.6, they are the same. So they are balanced. Right, so let's go to 2 more questions. Oh, I spelled wrongly. Okay, it's going to make it harder. Exam style. All right, so question 9. Question 9 is about speed. Draw 1. 10 is also about speed. Draw 1. Car travels 100 meters in the first second. 180 meters in the next 20 seconds. What is the average speed? What's the average speed? Okay, 9 is what? A passenger sit inside a train moving. Okay. What is the relative speed of another train? Okay. Question 10 is a similar questions. The one that we had just now. Right? Hurry up, hurry up. 2 more questions, then we are done. Fry your brain a bit. Nice. See? Then is also C. What about Jaden? What do you think? Okay. I also think it's C. Right. Elise, great. So question 10 is similar to the one that you missed just now. Now you understood. So you learn how to reply this type of questions, how to answer this type of questions. Let's see whether the answer is correct. Both correct. Excellent. By the way, this is a harder question compared to the previous few chapters. So I think on average, you still did well, about 7 or 8 out of 10. Okay? Thank you very much. And I'm going to see you after the Eid holiday. Enjoy your holiday. Bye-bye.
Bye bye.
Bye-bye.
Thank you.
Thank you.